Well, we're going to take a look at section 1.2. And section 1.2, we're starting to solve some equations. We're going to look at some specific ones. The first type of equation is the form ax plus b, 0. Now, the solve for equation, what that means is we want to get x by itself. So what's this idea of getting x by itself? Well, let's say we have something like this. Let's say we're going to solve this equation. The way we can think of this, think of a scale where the equal sign says the sides of the scales are balanced. In other words, they weigh the same amount. So there's some mystery weight x. And let's say we just have a pile of sand. Pile here weighs 3 pounds. And on the other side, there's a bigger pile of sand that weighs 5 pounds. So using the scale to figure out how much x weighs, we can brush away the 3 pounds of sand on this side and brush away 3 pounds of sand on the other side. As long as we brush away the same amount on each side, the scales stay balanced. Now, if we have 5 pounds of sand and we remove 3, we're going to have 2 pounds of sand. And since we remove the same amount of weight on both sides, well, the scale's still going to stay balanced. So this unknown weight is balanced by 2 pounds of sand. So that means x is the same as 2 pounds. X must weigh 2 pounds. So this is the idea of solving for x. We want to get x by itself. And then as we use various techniques to do that, we're going to get some number on the other side. And as long as we do to one side as we do to the other, it's going to stay balanced. So eventually we'll have x by itself balanced or equal to some number. So here's the key thing when we do algebra. What we do to one side, we must do to the other. Now, the way we're going to solve for x, we can do this in a shorthand. We don't have to draw scales every time. So our x plus 3 equals 5. So this is the x weight. Here's 3 additional pounds of sand, and this is balanced by 5 pounds of sand. So now we remove the 3, remove it from both sides of our scale. It's balanced. And so here we have a plus 3 and a minus 3. When we do the opposite of adding, which is subtraction, these cancel out. So we get our x equals 2 pounds. Now this cancellation, we're going to use this a lot. And the way we cancel is we use opposites. So in this case, since we were adding 3, we do the opposite, subtracting 3. It's sort of like if you have $3 and then you lose the $3, you're to 0. Or let's say you go into debt $100. Oh no. But then you get $100. Well, then now you're back to 0. Subtraction, go into debt. but then do the opposite, add the same amount, and that brings you back to where you started, 0. So here we're adding 3. We want to make this into 0. We do the opposite. We subtract 3. So when this becomes 0, that just leaves x by itself. But to keep things balanced, we also have to subtract 3 from the other side. So we get x equals 2. So let's take a look at opposites. Let's look at how we cancel things. So first off, addition and subtraction are opposites. They undo each other. They cancel each other out. Also, multiplication and division, those are also opposites. They cancel each other out. So let me show you how this works. You've already seen a little bit. But once again, let's say we have this. X plus 2 equals 10. We want to get x by itself. So we want to do the opposite of adding 2, subtract 2. And what we do to one side, we do to the other. And so we get x equals 8. Well, let's consider this. Let's use a different variable. Let's say y. Y minus 5 equals 7. To discover y's identity, we want to get y by itself. So we add 5 to both sides. These cancel. And y is equal to 12. So addition and subtraction are opposites. They go together. Now you might recall in algebra, when there's a number next to a variable, it means multiplication. So we want to do the opposite of multiplication. That's division. So we divide both sides by 7. X equals 3. Now consider this. X over 4 is equal to 5. Now, this means division. So we're dividing x by 4. So to undo the division, to cancel it, to get x by itself, we multiply both sides by 4. These will cancel. X, again, what we do to one side, we do to the other. X is equal to 20. So those are sort of the basic cancellations. Now, ax plus b is a little more complicated. Let's recall PEMDAS. Remember, it's the order of operations. Parentheses, exponents, multiplication, division, addition, and subtraction. Now, multiplication and division we treat as equals. So we take care of calculations in the parentheses first. Then we compute exponents. And then with multiplication and division, we just do the one that comes up first and then the one that comes up next. And if it's division, that's fine. If it's multiplication, that's fine. But the way we approach it, we go from left to right in our expression. We go here, when we multiply, divide, divide and multiply until we reach the end. Same with addition and subtraction. They're treated as equals. And we also compute these left to right. So we just add, subtract, subtract, and add from left to right until we're done. Now, for arithmetic, we do this. We start from the top and we go to the bottom. But when we're solving for x, we're going to cancel things, but we cancel going in the opposite direction. Now, it could be x, it could be y, it could be t, but we'll just stick with x for now. And as we go backwards, dealing with addition, subtraction, multiplication, division, exponents, and parentheses, well, how we're dealing with them, we're canceling them. So we'll cancel addition and subtraction, then cancel multiplication, division, cancel exponents, cancel parentheses. Now, roughly, this is what we're doing. Now, there's some ways you can alter this. There's things you can do. For example, with distribution, with parentheses, you can use distribution to get rid of parentheses. But you could also, stick to this backwards order if you want as well. So we're going to do this. So that means when we have ax plus b equals 0, or minus, we're going to cancel this first, and then cancel this multiplication to get x by itself. You can think of it as we're reversing the process. If we knew what x was, we would follow PEMDAS, multiplication first. And if we know what x is, we would have a number. And then we would add b, and that would be it. So to solve for x, we're going to go backwards, cancel. We'll cancel the addition of b. We'll cancel the multiplication of a, and that is going to give us x. All right. So we're just reversing the process we get from following order of operations. So for example, say we have this. There's a multiplication and a subtraction. So by order of operations, if we know what x is, we do the multiplication, and then we do the subtraction. So to solve for x, we're going to go backwards through the order of operations, canceling as we go. We'll cancel the subtraction, and then cancel the multiplication. We use opposites to cancel. So the opposite of subtracting 5, adding 5, make sure we do it to both sides. Opposite of multiplying by 7, dividing by 7. So we get x equals 11. Now, a trick we can use is distribution. So how does distribution work? Well, let's say we have this. Three times x plus 2. Now think what multiplication means. Like, for example, 3 times 5. Well, that means you add 5 up. Well, you add 3 5s up. You add 3 5s together. So in this case, we're going to add 3 x plus 2's together. Oh, addition. So what happens here, we're going to use a trick. Addition has two special properties, associativity and commutativity. Now, commutative means the order doesn't count. 5 plus 3 is the same as 3 plus 5. You're going to get the same answer. So that's commutativity. Associativity, here, let me write that down, what that is. The order doesn't matter. Now, the other property is associativity. This is where parentheses really come in. We use parentheses to group calculations. Like I want to group this addition or these two elements, group these two elements. And associativity means the parentheses don't matter. So 2 plus 3 plus 4. Add these two first, you'll get 7. 7 plus 2 is 9. But if you move the parentheses, 2 plus 3 plus 4, you're going to get the same answer. 2 plus 3 is 5, plus 4 is 9. So with addition, the order doesn't matter, and the grouping doesn't matter. Now, this is only true with addition and multiplication. Once you start throwing subtraction and division, not going to work. Subtraction and division are not commutative, and they're not associative. Multiplication and addition, those are commutative and associative, not multiplication and addition. But, I'm sorry, multiplication and subtraction. I'm sorry, not division and subtraction. Addition, multiplication are commutative and associative. Subtraction and division are not. With subtraction and division, the order does matter. So, for example, 3 minus 2 is 1. But 2 minus 3, if we switch the order, it's negative 1. So subtraction is not commutative. Also, if we have 4 minus 3 minus 2, this will be 1. 4 minus 1 will be 3. Now let's switch the order. 4 minus 3 minus 2. Not switch the order, but switch the grouping. This will be 1. 1 minus 2 is negative 1. Unlike addition, order matters for subtraction, and grouping matters for subtraction. It matters for division also. So we're adding here. So that means the order and the groupings, they don't matter. So we can just rewrite this as say x plus x plus x plus 2 plus 2 plus 2. With addition, we kind of don't have to follow the parentheses. And then we take a look. There's 3 of these. There's 3 of those. So we could rewrite this. Again, repeated addition is multiplication. 3 times x plus 3 times 2. Now, mathematicians look for shortcuts. We don't want to do this every single time. So what we'll do, we'll write it like this. And that's what we mean by distribution. It's a shortcut for all of this. Now, you might wonder, how does this work with subtraction? It actually does. We have to do a trick. The freedom we get here that addition gives us, we don't have that with subtraction. So we got to do a little modification. We can rewrite this as adding a negative. If you think about it, 5 minus 2 is 3. 5 plus negative 2 is also 3. So we can rewrite this instead of x minus 2, x plus negative 2. And now we can use our distributive rule. 3 times x plus 3 times negative 2. And we know this is going to be negative. That's going to be negative 6. And now remember how we said subtraction is adding a negative? Well, we can say adding a negative is subtraction. And then 6 is 3 times 2. So what we can do, again, let's take that shortcut. Let's just say 3 times x minus 2 is 3 times x minus 3 times 2. So even with a subtraction in here, we can still distribute. And we can distribute negative numbers. We can also distribute minus signs. So we have a negative number that could multiply to these. We have a minus sign that acts as the opposite operator. In other words, it makes positive things negative. It makes negatives positive. We can distribute a minus sign or an opposite operator just as well. So let's do some distributions. All right. So we've got some distributions to do. Now, we can distribute this 3 like this. I had a student who came up with this idea where you have the arcs coming out like that. It shows you where your distribution is going to happen, or how this number is going to, which elements it's going to attach to. And it attaches through multiplication, in this case. Now here, we're going to distribute the 4 with the minus sign. And in this case, we're just distributing a minus sign. going to act like an opposite operator. So we'll get a minus x, but then minus and minus, that becomes positive. We're going to get minus x plus 2. So here we'll get 3x minus 12 minus 4x minus 4 times minus 3 is plus 12 equals x plus 3 minus x plus 2. Well, now we're going to combine like terms. And like terms kind of works like this. We'll take a little break here. 2x plus 3x. Well, remember multiplication is just repeated addition. 2 times x means x plus x. 3 times x is x plus x plus x. So this is x plus x plus x plus x plus x. Now we have repeated addition, and there's 5 x's. So that means we can write this as 5x. And again, being savvy mathematicians, we look for a shortcut. We'll just say, well, 2x plus 3x. We'll add the 2 in the 3 to get the 5 and keep our x. Shortcut. So now let's go back to this. So we're going to combine like terms, and x's are different terms from, say, constant numbers. So we've got 3 x's, then we lose 4 x's. So we're going to turn out to be in debt 1 x, or minus a single x. And then we have a negative 12 and a positive 12. Well, that's just going to be 0. I'm just going to put plus 0 here. You can do minus 0, plusing or subtracting 0. It's the same thing. In fact, because this becomes 0, just leave the 0 off. It's just nothing. Now over here, we have an x and a negative x. It's like having $1. You lose $1, the x's cancel out. So there's a 0 there. Then we have a 3 plus 2, which is going to be 5. So there's a number of things you can do with this. At this point, we could use the opposite operator, again, on both sides. So those cancel. Get x's, negative 5. Another way of seeing this, you can treat this as negative 1 times x. And then divide both sides by negative 1. And so this gives us x equals negative 5. And the same answers we have. All right. So distribution, the power of distribution, the reason we do it has to do with PEMDAS. When you see parentheses, it says, got to do it in the parentheses first. But when we have a variable inside the parentheses, so let's say we have our something like this. According to PEMDAS, we need to do this first, but we can't. We don't know what x is. Now, x is a number, but it's unknown. And we can't perform addition until we know the numbers we're adding. So we can set it up and say, well, someday when we know what x is, we'll do this computation and then multiply by 3. I guess we're in a holding pattern until we find out what x is. Well, we're solving for x to begin with, so that's not going to do us any good. So distribution, by distributing, again, we're allowed to distribute using the properties of addition that say you can ignore the parentheses. This gets rid of those parentheses. It takes away that obligation from PEMDAS, and it lets us move forward with the problem. And so we can turn this into 3x plus 12 without parentheses. And so we can continue on. So that's the power of distribution. Let's see. Let's say we have this. How do we solve for x in this case? What we want to do, we have these fractions with denominators. We want to cancel denominators. And the way we do this, we're going to multiply through by what's called the lowest common denominator. Or the LCD. Now, how do you find an LCD? Well, it goes down to what's called a prime factorization. So prime numbers, they're sort of like DNA for a number. For example, 14 is 2 times 7. Now, 2 is the only even prime number. 7 is an odd prime number. And the product of those two primes gives you 14. So we want to take each number and break it down into a product of its prime numbers. So let's say we want to find the LCD of 14 and 21. So the first thing we do, let's list out the prime number. And notice I'm using colons and not equal signs. So 14 is 2 times 7. 21 is 3 times 7. So the way we find the LCD is we make this listing of numbers the same. We want to make these the same. So this is a 3 times 7, but it's missing a 2. Put in a times 2. This is a 2 times 7, but it's missing a times 3. Put in that times 3. Now these two listings are the same. And what are they equal to? Now we use the equal sign. It's going to be 42. So 42, basically what this is going to mean for us. If these were denominators, if we multiplied through by 42, 42 is the smallest number that will cancel those denominators. Well, let's see it in action. So 42 in that example was the LCD. Now let's take a look at this. The denominators are 2, 5, 10. So what are the prime numbers here? Well, 2 is already a prime number. Don't have to multiply anything to it. It's already prime. Same with 5. It's already prime, so we don't need to multiply anything with 5. 10 is 2 times 5. So we need to make these 3 listings the same. So what's this one missing? Well, it's missing a times 2, that's for sure. And this one's missing the times 5. So 2 and 5, 2 and 5, 2 and 5. The order doesn't matter. Well, we got it. So the LCD for these 3 numbers will be 10. So when we multiply through by 10, 10 is the smallest number that will cancel the 5, the 10, and the 2. So let's multiply through. We'll have 10 times 3x over 5 minus 10 times x equals 10 times x over 10. And then we're going to have 10 times 5 halves. So this is how this works. We're going to take the denominator and divide it into the LCD. So 5 goes in the 10 2 times. This is just going to be 10 times x. 10 goes in the 10 1 time. And 2 goes in the 10 5 times. So what this gives us is, instead of 10 times this, the 5 dividing into 10 makes it a 2 times 3x minus 10x equals 1 times x minus 5 times 5. And here, let me do a different pen here. So we do our multiplication. 6x minus 10x equals x minus 25. Now these we can combine 6 x's and we lose 10 x's, so we're in debt 4 x's. So that's minus 4x. And then we have x minus 25. And we want to get the x's on the same side. So let's cancel this x, adding an x. The opposite would be subtracting an x, just like you do with a number. But what you do to one side, you've got to do to the other. Canceling this x makes it go away. We only want x to appear on one side. So minus 5x equals minus 25. Finally, we're multiplying by negative 5. Divide by negative 5. We'll get x equals negative divided by negative is positive. Positive 5. So what we do with fractions, we're going to do the same thing with what are called rational functions or rational equations. Let's see. So let's say we have this. Maybe there's a slightly different one. Oh, I'm going to change it up just a little bit. There we go. And we're supposed to solve for x. Same trick. Cancel denominators. And we do this by multiplying through by an LCD. So how do we find the LCD here? Well, what we want to do is we want to look at this as products of first degree monomials. Now, first degree means it's the variable doesn't have a square. That means it'd be second degree. There's no x cubed. That'd be third degree. It just has x. That's first degree. And you're going to have some kind of binomial. So that means it's going to be x plus a 3 or a y plus a 2. We want to come up with products of these. Let me show you. So let's list our denominators. So a first degree binomial, it's already there. X plus 3. There's no square or cube on x, so it's first degree. And then it's a binomial, so we're okay. X plus 3. It's kind of like a prime number. Now this one, you can actually factor out a 2. When you do that, you're going to get x plus 3. This one, it's first degree, binomial, nothing will change. So we've written this in terms of, okay, you can have a constant in there, that's all right. But it's in terms of first degree binomials. So now, just like with the numbers, we treat these first degree binomials like they're prime numbers. Well, now we got to make the listings the same. So what's this one missing? Well, it's got an x plus 3, but it's missing a times 2. It's also missing a times x minus 2. Now this one has the 2 and the x plus 3. It's missing an x minus 2. This one has an x minus 2, but it's missing the 2, and it's missing the x plus 3. And now the listings are the same. There are the same first degree binomials and the same constants that are floating around. And a floating constant would be like this 2 here. So this means the LCD is 2 times x plus 3 times x minus 2. This is the simplest expression that we can multiply through by to make these denominators cancel. Well, let's do it. And then usually put dots for multiplication, but I'm going to leave those out. But we'll put one for here. Now I'm going to factor out this 2. 2 times x plus 3. I'm going to say pro tip. Factor out a constant if you can. Well, factoring generally is going to help. There's a problem in here. We have to get x squared plus x minus 6 as a denominator. Factor that x squared minus x minus 6. Factor that first, and then construct your LCD. So now let's look for cancellation. Well, here, x plus 3 and x plus 3 are going to cancel. Over here, the 2 will cancel, and the x plus 3 will also cancel. And then here, the x minus 2, that goes away. So what are we left with? Double check this real quick. Looks good. All right. So this is it. It simplifies down really nice. So I'm going to combine these to get 6x minus 2. This will be 5 times x minus 2 plus 1 times 2 is 2x plus 3. And now we just have to distribute. So that'll distribute. That will distribute. And this will distribute. So we get 6x minus 12 equals 5x minus 10 plus 2x plus 6. Now, there aren't any like terms that combine on the left, but we do have like terms to combine on the right. So 6x minus 12, 5x's plus 2 more x's, 7x, negative 10 plus 6, negative 4. And we want to get the x's on one side, so I'm going to cancel this positive 6x by subtracting 6x. And subtract 6x here. So there's negative 12 equals x minus 4. Finally, to get x by itself, the opposite of subtracting 4 is adding 4. So negative 8 equals x. And that's going to be your answer. So the last thing to talk about in this section, it's what we call types of equations. And the type that we've been working with so far is called conditional. That means there's at least one solution to the equation. Now, we talk about this in terms of solution sets. Now, a set is a collection of objects. So when we talk about a solution set, it's a set that's a collection of the solutions. So the solution set contains at least one solution. So this is what we've been doing the whole time. Now, for example, we're going to solve for x. Well, again, we're going to cancel addition, subtraction first. Then we're going to cancel multiplication, division. So we'll get 7x equals 49. We divide both sides by 7. We'll get x is equal to 7. And the way we express this with a solution set is we have a set. Now remember, a set has these curly braces. This is the set. It's like a container that we throw things in. And we place our 7 in that solution set. So this would be a solution set for our equation. Now, this solution set contains only one solution. They could contain more. So let's say we have this. Let's factor this. If we factor this, it becomes this. And in this case, if we let x be 2, 2 minus 2 is 0, this whole thing gets zeroed out. So one of the solutions is x equals 2. If we let x be 3, 3 minus 3 is 0, 0 times this is 0, it zeroes everything out. So another solution is x equals 3. So in this case, there are two solutions in our solution set. Conditional equations have at least one or more solutions. Now let's take a look at a different one. Inconsistent. So for an inconsistent equation, this means the solution set doesn't contain any numbers. It's empty. And When a solution set's empty, you can write it. It's just curly braces that don't contain anything. But there's a special symbol that we use. The special symbol is a circle with a slash, or what we call the empty set. Now, an example of one, let's say we have this. This equation. Now, is there a number you can think of where that number is equal to exactly the same as itself plus 2 more? Think about it. Is there a number that, or quantity, that is equal to the same quantity plus 2 more? Is $7 equal to $7 plus 2 more dollars? No way. And if you try to solve for x, you'll get sort of a weird result. So you want to get all the x's on one side, so let's cancel the x over here. And what we do to one side, we do to the other. Well, this is x minus x is 0. That cancels, or 0. So it's just going to be 0 equals 2, and that's not true. So this means we have an inconsistent equation, and so the solution set is empty. So we use the empty set as our answer. Now, the last type of equation is called an identity equation. For this equation, the solution set is all real numbers. It doesn't matter what number you pick, it'll always work. The equation will always be true. So for example, let's see, here, let me pull one out of here. There's a good example in the text. Let's see. There was a good example. Well, I'll just come up with one. Something like this. So if you simplify this down, combine like terms, we'll get 3x is equal to 3x. And you can, subtract 3x from both sides. We can do that. We subtract 3x from both sides, we'll get 0 equals 0. We could divide both sides by x. So this one we subtract 3x. We could divide x. I got to be careful here. I want to mention something. Most algebra books kind of take this for granted, like dividing x and dividing y, but usually need to state, because x is an unknown number, we need to make sure it couldn't possibly be 0. You don't want to accidentally divide by 0, because you can't do that. So let's assume x can't be 0. So you would get 3 is equal to 3. Or if we divide both sides by 3, we'll get x equals x. The point is, when you have an identity equation, you're going to get a simplified result that's invincibly true. 0 is equal to 0. 3 is equal to 3. X will always be equal to itself. So this is how we know we have an identity equation. It's invincibly true no matter what choice we make for x. So if we get something like this, you can just say, okay, that's an identity equation. What really shows through, though, this right here. x equals x. Choose any real number, it's always equal to itself. So, or you can just back up here. 3 times any real number will always equal 3 times that same real number. Doesn't matter what number you choose for x, this is always going to be true for any real number. Just not for just a few of them or one of them, any of them. This is going to be true. So the solution we put here for all real numbers is the interval minus infinity to infinity, or you might just type or select all real numbers. So I want to look at one other question. It's just kind of a peculiar one they have in the text. Let's say we have this. I want to solve y1 equals y2. All this is saying is we're going to take this expression and set it equal to that expression. y1 equals y2. And then we just solve for x. So we'll be distributing these 5s. Combine like terms. Get x's on one side. So we'll cancel that 5x by subtracting 5x. And again, what we do to one side, we always do to the other. Add negative 42 to both sides. Finally, divide by 5. And we'll get x equals 6. So the last thing to mention in this section are restrictions on x. So let's say we have this equation. Now, what we need to do for this, I'm just going to set it up, but you need to find the LCD. Now, again, factor this first. So we have x plus 3, x minus 2. And if we factor this, x plus 3 times x minus 2. So these are first degree binomials. Now this one is already there. First degree binomial, product of two first degree monomials or binomials. So now we ask the question, what is missing from these listings? Well, this one needs a x plus 3. This one needs an x minus 2. So now they're all the same. So the LCD, what we're going to multiply each of these by, remember you want to factor this so it looks like this. X plus 3, x minus 2. Multiply this, to this, and to that. Now, the thing I want to talk about are restrictions on x. Values x cannot be. Now, by multiplying through by the LCD, we're going to discover the values of x that make this equation true. Hopefully this is a conditional equation and it's not an inconsistent equation, one that doesn't have a solution. Hey, maybe it's an identity equation. You'll have to find out. But there are certain values x definitely can't be. And those are values that will cause a division by 0. So again, it helps to factor this. This factors to be and we can see what would cause this to be 0. Well, if x was -3, -3 plus 3 would give you 0. So -3 is one of the values x can't be. Another one, x minus 2 here. If x is 2, you get 2 minus 2, that becomes 0. That means x also can't be 2. In same story over here. If x is -3, -3 plus 3 is 0. 0 times, I mean, it'll be -3 minus 2, but it doesn't matter. This is 0. 0 times whatever this number is makes everything 0. Get division by 0. So again, we can't do -3. Same with x is 2. Doesn't matter what the 2 plus 3 is 5. 2 minus 2 is 0. 0 times this is 0. Get division by 0. So again, x cannot be 2. So one of the questions that comes up in this section is, can you identify which values x cannot be? Well, that's it for this section. If any questions, let me know. I'll try to get the next section up as soon as possible. And hope you're having a wonderful day.